Good morning. So, after a long time, I'm back again with another topic from the chapter Electrostatic Potential. The other introductory videos of this chapter will be covered by me in a later session, in a later series of video. Obviously, right after I upload this, I'll be uploading every other videos related to the same subject and every topic that comes before this. So, the chapter we are going to study today will be the electrostatic potential. Electrostatic potential. So, electrostatic potential is a very important concept is actually a central concept in physics, especially in electricity and magnetism. The term potential is a very commonly tossed around term in physics. You might have heard about potential first in your 9th standard or even in your 6th or 7th standard CBSE, where you associate the term potential with something hidden inside or something which is kept hidden, or it is kind of like something that is stored. So in that terms you might have heard about the potential energy. So potential energy is one term. Where you have learned that potential energy is a form of energy that is stored, a stored form of energy. Okay. Electrostatic potential is almost a similar concept, where the stored energy, we have something known as electrostatic potential energy. It's not electrostatic, it's electrostatic. So electrostatic, we have the electrostatic potential energy. And so the concept of electrostatic potential is a bit different from electrostatic potential energy, but basically both are similar in terms, because potential energy, the basic difference between potential energy and the potential is that potential energy is the energy of a particle or of a system. System could be a single particle, and we have a system could be a bunch of particles, a lot of them, a lot of particles. So it can be either a single particle or a lot of particles. But what is potential? Potential is basically it's a field. It's in fact a field. It's a scalar field. Or if you are more familiar with your algebra, I can call it a scalar function. So basically it's a mathematical quantity. A potential is mathematical. More often it's considered to be a mathematical thing, and whereas the potential energy is something considered to be real or physical. Okay, so how are they both connected? See, let me first of all just remind you, as if you have learned my previous lectures, but which are not yet uploaded, but still let me tell you what potential or this scalar field thing or scalar function thing is. In your class 11 of CBSE, you have gone through the chapter of gravitation. We had studied gravitation. In gravitation, if you had a piece of mass or a system of mass which had some mass m. You do not know how it is or how its shape or size is, but only factor you know is its mass. Now there is this concept called the center of mass, and from this point, the so-called center of mass O, you may assume your coordinate to be fixed at this O and your origin to be at O. Suppose, you could be anywhere else also. You are just an observer, so you could be at any point. There is this freedom for you to be at any point in the space. But for the sake of convenience, suppose, let us say, you have fixed your coordinate system at the center of mass of this body. Now every point in the space, a point this, it could be this, it could be this, any point among the infinite sea of points in this space, in the space around the given mass, you can draw a position vector to that point, and you can call that position vector r. So suppose this was your point, and let that point be, say, h. Why should we stick on to using only p? So I'm just calling that point to be h. Obviously alphabet is not enough to indicate all the points, so basically you are doing is you're drawing a coordinate system. It could be a 3-dimensional coordinate system, 2-dimensional, whichever kind of living being you are. But in this case, our computer screen, which is a 2-dimensional array, will have always a 2-dimensional address, and which is indicated by the pixel number with respect to some origin. I don't know, maybe it's at either one of the 4 corners. Okay, let us not get into too technical details, but anyways, this point h, what I mean is this point h is one among the infinite number of points in this sea of points. So h can have a coordinate value. It can be some x, some y, some z. We do not know yet. And the vector r is itself in fact represented using these coordinates. So my point is, the key point here is, due to this mass, this entire blue bulb of mass, you can have a gravitational force. Since this point h is under the influence of the gravitational force of the given mass m, it's in its field. So there at the point h, you can associate a gravitational force, and which will be obviously a function of r and also the mass m. So the functions form would be complicated and dependent on how the m is distributed, but still there you can associate a force value. Likewise, at any point around this mass, let this point be q, let another point be I don't know, a, there is another point b, and at any point in the space around, you can associate a function f, and the value of function f depends on r and m. R is the distance from the center of mass, the direction, as well as the mass m itself. So all this force does is it tries to attract you towards the body. So whenever it attracts you towards the body, it's actually happening naturally. And also, as you move towards the mass, any object kept at any of these points, when it starts moving towards the body, what happens? It starts to accelerate. When it accelerates, its velocity keeps increasing. If its velocity keeps increasing, which means its kinetic energy keeps increasing. So since kinetic energy and velocity are proportional to each other, and that too they are dependent on the square, kinetic energy is dependent on the square of the velocity. So as you can see, kinetic energy increases. So where did that object get its kinetic energy, or how how in the world is its kinetic energy increasing if there were no kinetic energy to start with at first? See, it all converts to the fact that the particle, whatever object you had here at the point B, say at point B or at point H, had something known as its potential energy, a gravitational potential energy. So how do you measure the gravitational potential energy of some small mass which was at any of these points? It's easy, because all you need to know is the mass, as well as one more thing. See, let me just redraw that our bigger mass m. So we had this bigger mass m, and let this be the point H. So at the point H, even before placing the mass m, there was a gravitational field, and that gravitational field was actually force per unit mass. So this is your gravitational field here. I don't know how to represent gravitational field using maybe I can just use something like I don't know, maybe I can call it G. I don't know, G, is that even a proper symbol? I don't know, maybe, yeah, okay, fine. Anyways, G was actually the force per unit mass. So that's the gravitational field you are associating, and that is what it is. So what happens? The potential, the value of potential. What do you mean by potential then? See, potential is similar to the field itself. I mean the gravitational field itself, but it's in fact not a vector, but at the point H you will have a value associated to the potential, a potential due to the distance and mass. Potential which is the function of distance and mass, obviously. And it's not a vector, because at any point you can associate a number. You are going to associate a number here at this point, say H. Let me call this point I. The point I has a different potential value because it's at a different distance, r prime. See, H was at a distance r, and I was at a distance r, vector r prime. I don't know, I can call it that. You can have a different value. Now what is potential? Potential is this function, and it's a scalar quantity. It's just associating a number, a single number. You can attach a single number to every point. Okay, you can attach a single number. And what does this number give you? This number at that point means, what does it mean? It means it is the amount of energy, specifically what form of energy? The amount of potential energy, or let me just cancel the potential and let me just make use of energy alone. It's the amount of energy required to unbound a mass, a unit mass, specifically a unit mass. So what is potential? The value of potential V at that point is the amount of energy required to unbound a unit mass from there. So you might be confused, what does this unbound mean? Unbound means if you had this point H and you had a mass, you had some mass, say, I don't know, a very massive object, no, not a very massive object, but a unit mass. You had a unit mass, a mass which is equal to 1 units in whatever system you follow, and in that unit and that particular system your mass was 1 unit, and that mass had to be unbounded from that point, which means you had to move it from H to infinity. So that is how you make things unbounded in gravitational system. So if you wanted to unbound it, you had to move it from that point to infinity. That's what it means. So that is the energy. So the number here, the V here at H, means It is the amount of energy you would require the mass, the unit mass, to uh, get unbounded from that point. So that is what it means. So similarly, so which means if you had a point and the value of potential, this V is actually in fact the representation of potential. Suppose you had a point, and that at that point the potential value, there was a value for potential, and let it be some certain values. So that means here the V is actually energy required to move a unit mass. So we will have units of joules per kilogram. Okay, since I am following the SI unit, I am going to use kilograms. Suppose this point had like 45 joules per kilogram, which means to move a unit mass from here to infinity, you had to apply 45 joules of energy. Just for one unit mass, the energy is 45. What about if you had 3 units of mass? At this point, you had 3 units of mass, which means you had 3 kilograms of substance at that point, and you wanted to move that point from there to infinity. How would you calculate the energy required? You know, out of this 3, each kilogram requires 45 joules. So you had 45 joules for 1 kilogram, 45 for the other second one, and 45 for the third one. In fact, you require a total amount of energy which is equal to 3 times 45, and that's going to be around 135 exactly. So 135 joules of energy, if I am correct. Let me just check if I am correct or wrong, because I'm a very poor guy at multiplying numbers. Yeah, exactly, it is 135 joules. So whatever be the mass, here I use 3 kilograms as an example. The mass could be I don't know, a random number m. So if this is you had m kilograms of mass, then you would require m times the value of the potential at that point, right? So it is like 45 joules per kilogram. So that much energy is required to unbound it. So which means if that particle is exactly at that point, what is the amount of energy it has? It is same as this. It is same as this. Oops, I'm so sorry. Okay, it is the same as this, which means you had this point, and there was a value V at that point, and you had a mass m at that point, a small m mass. You had a small m mass over there at that point. What is the potential? Potential is the energy required to move it from there, which means that is the energy you need to supply. You need to supply that much of energy, and that energy is equal to m times V. Okay, this V is not velocity, it's actually potential. Okay, this is the energy you will have to supply to move it. So which means the energy, if the system is static, which means it is not moving, it's just there. If it has zero velocity, which means velocity is 0, so it's a static system. So it's not moving, it has no other energy. Why should you apply a system? Why should you give energy to a system which is static already, and to unbound it, which means it already has some potential energy, and this energy you apply is actually the potential energy of the particle at that point. So this is the point at a distance r from the very massive object. So that is the potential energy. mv is the potential energy of the mass small m at that particular point, because of this heavy massive configuration, this gravitational configuration. Okay, similar to that, I don't know what is the underlying secret behind such a symmetry between charge and mass, but there has to be something, but I am so unqualified to talk about it. There is this mass and there is this charge. So mass and charge both are scalar quantities. Actually, the source of charge can be traced to certain facts and principles in quantum field theory, which is not of your level, so I'm not going to deal about it. So if you want to pursue any study about charge, you can just go and study quantum field theory, which is one of the best theories we have yet. Okay, so quantum field theory is the one of the best theories we have yet, and also deals with most advanced subjects of particle physics and all that, but I'm not going to deal with that right now. Okay, so there is some connection, there is some symmetries between mass and charge, but anyways, about charge, it was mostly Coulomb and other prominent physicists and engineers who had worked on the concept of charge, whereas the concept of mass was mostly dealt by Newton, Bernoulli, Poisson, and other uh, famous mathematicians or the natural philosophers back in 16th, 17th, and 18th century. Mostly concept about charge was dealt in the 18th century or so, if I am correct. And I might have also messed up with the pronunciation of these people, these huge giants. I mean, huge giants, not huge giants, but giants, obviously. All right, so similar to that, if you have a charge configuration and you have space around it, and let me just choose a point here, and I call that point M. At this point, you have this electric field, and the electric field at this point, I'm not going to indicate the arrow, so I'm just going to say there is an electric field. That electric field could be at possibly in this direction, because this charge configuration may not be a point charge, it could be anything. So due to this charge, the electric field at M is so and so. Similar to electric field, I can associate one more quantity at the point M, and that particular quantity which I want to associate is called the electrostatic potential, which itself could be a complicated function of the distance vector r, the position vector r, as well as the charge q. So it's a very complicated function. Obviously it can be, I do not know, I mean, charge, total charge, or I don't know if it is the charge could be represented using any of these. Okay, it can be charge itself, or it can be charge densities. So the function may contain charge densities as well. So anyways, it's in fact charge which we are talking about. So that's it. So the potential, there you can associate a number called electrostatic potential here, and that number, what does that number do? That number, similar to in the case of gravitational potential, electrostatic potential refers to some sort of energy required. Okay, some sort of energy required at this point M. If you have a unit charge, see, let me just go on and point out. See, this was our point M, and there is a value of potential V at this point M due to that charge configuration. Okay, now at this point M, if there is a value for the electrostatic potential, and we call it V, what does that mean? It means you have a unit charge. It's unit in your standard of measurement. Okay, in my case, SI unit is the one which I am going to use as a standard. So I will be using a unit charge. In my case, would be 1 coulomb. Okay, in my SI unit, it is, I mean, not my SI unit, but in the SI unit that I am measuring is going to be 1 coulomb, the unit charge. So whatever is your unit charge, okay, whatever is your unit charge, if it is here, I mean, the V is actually the amount of energy. It's again the amount of energy required. See, in this case, in our case, we are talking about charge systems. So charge systems are both attractive as well as repulsive. So V is the energy required either to assemble means to bring that charge there, or to disassemble. If I am correct, disassemble, I mean disassemble, there is only one S, disassemble. So it is the energy energy required to either assemble or disassemble a unit charge from that point to I mean that from that point. So here assembling and disassembling means, see, if you have say if you have three charges like this, now they're already bound to each other. Okay, say they are bound to each other, but then what does disassembling means? Suppose this was q1, this was q2, and this was q3. Disassembling means you take them apart to infinity from wherever they are standing right now. So they are standing at these 3 points, and they, if you mean to disassemble, you want to bring them, I mean take them away from their positions to infinity. That's what disassembly means, just like getting it unbound. You can use the same term here also. Now what does assembling means if you had these three charges kept at infinity and you are bringing them from infinity to their present configuration. Okay, so you are bringing q1 from this side, which was at infinity, and q2 from this side, which was also at infinity, and q3 from this final side, and which was also at infinity. So you are bringing all these and you are placing them at those particular points and you are making them bound. So this is called assembling. So assembling and disassembling, both these may require a certain amount of energy. So that's what it means. See, let me just take an example for this case. So at this point, suppose I don't know where the source charge is kept right now. Okay, I don't know where the source charge is because I don't mind right now. And suppose this point was m1, and suppose this point was m2, and there we had another point m3. There is some sort of charge configuration somewhere, and we do not care. But due to that charge configuration, at point m1 we had a potential v1, which means that is the amount of energy you required to move or to assemble a unit charge. Okay, to assemble a unit charge to that point, that was the amount of energy, and there is v2 potential over there and v3 potential here, and I assume these three particles are non-interacting. Okay, they do not interact mutually. In that case, this v1, v2, v3 are fixed values, and so what happens, if you wanted to keep a unit charge over here, the energy required was v1. A unit charge over this point, it was v2, and to place a unit charge at the point m3, the energy was v3. So these are the energies required for unit charges, single unit charges. What about if you had 4 units of charge and you wanted to keep them here from infinity? Okay, every time whenever I'm bringing the charge units, I'm bringing them from infinity. So if there is 4 units of charge, to keep it at v1, the energy required would be 4 times v1, because 1 unit requires v1, so 4 unit would require 4 times v1. And what about here? If you had 3 units, you would require a total of 3 v2, and here if it was like we wanted to bring 2 units of charge, it would require 2 v3. So that's the amount of, that's what it means. So potential now is a clear concept. So potential means it is the value, the amount of energy required to assemble or disassemble a charge to that particular point from infinity, to assemble or disassemble a, not any charge but a unit charge. Okay, so remember, you want to assemble a unit charge. Okay, not any charge but a unit charge to this point, and that is the amount of energy that would be expended. So any unit of charge you bring in, any amount of charge you can bring into this point. You can bring 3 units, you can bring 1000 units, you can bring 50,000 units, nobody cares, but the energy would just be that number of units, n number of units times the value of potential at that point. So that's what it means. So that's the energy, that's the total energy you would get. So you would do is amount of charge times the electrostatic potential will give you the value of energy. All right, so these were a few concepts. So that was just an introduction. So let me now get into the content of today's video, which is it's also one of the most important concepts, because This concept is mostly used in engineering, I guess. I don't know if it's used in engineering. I mean, it suits very much for engineering purposes. So it's kind of like a thing. It's in fact real thing. It's very interesting. It's also very important and needy. And the concept that I'm talking about is about the. Let me use another color because you might be already bored by this blue color alone. Suppose you had I mean, the concept that I'm talking about is the equipotential surfaces. Equipotential surface. Let me go with the singular first. Equipotential surface or surfaces, whichever you prefer, because there are many of them. What are equipotential surface? So obviously from the name it suggests it's a surface. It's a surface. Equi, here the prefix equi refers to equal, and obviously you know what potential is. Potential is potential. Potential is the amount of energy required to move a unit charge or assemble or disassemble a unit charge. So you have equal, potential, surface. So there is a surface. A surface is a two-dimensional entity, not an entity. It's a two-dimensional mathematical thing. So here the surface is actually not an imaginary one, but it's just, it's there. We do not see it. It's invisible. It's actually sort of like a locus of points in 3 dimensions. So it's surface. It can be obviously a locus of point, could be anything like a line, a surface, or even an entire space. So here in this case it's a surface. A surface is actually it could be open surface, it could be closed surface. Closed surface, the best example of closed surface you might have studied are the Gaussian surfaces which you imagine. See, these Gaussian surfaces are not physical, but they are just imaginary. But equipotential surfaces have this physical existence actually. We cannot touch, or it's not a tangible kind of physical thing. Okay, it's not a tangible. Okay, equipotential surface. So the concept that we are going to learn is equipotential surface. As I mentioned, they have their own physical existence. They have their own physical. They are not actually tangible sort of thing, but they are actually a set of points in space. They're just set of points in space which form a surface. Equipotential, yeah, equipotential surface. Equipotential surfaces. So you can have many of these surfaces. So basically, where do you draw an equipotential surface? Actually, where you draw an equipotential surface is around a given charge configuration. Suppose you have a charge configuration. It can be anything. It can be a unit charge, it can be a dipole, it can be a messed up charge configuration, whatever it is. I don't care right now, because specifically we will be dealing with the type of equipotential surface later. I mean, sorry, type of the charge system and the related equipotential surface in a short. But what I basically mean is that if you have given a equipotential charge configuration, you can have something known as equipotential surface. You can associate with it. So how do you know what it is? So as I mentioned, equipotential surface actually stands for 3 things. It means equal potential surface. So it's a surface of equal potentials. That's what basically it literally means. It means surface of equal potentials. Equal potentials. How do you get that? How do you get to that? How do you know whether every point on that particular surface? So if you, so which means basically you have a surface, and there is any point, any number of points on this. There are actually infinite number of points on this surface basically. So at any point on this surface, say P1, P2, P3, etc., etc. So any point on this equipotential surface, okay, in this due to this charge configuration, the potential at each point will be the same, will be equal. So if you are at point P1, the potential at that point due to Q will be P1. sorry, V, and due to at a different point, say P2, the potential, if the point is on the equipotential surface, the value of potential will be V again, because it's an equipotential. So everywhere the value of potential should be same. So on this surface, at any point on this entire surface, the value of potential will be V. So this surface represents an equipotential surface. Okay, and where actually that surface did not exist. Actually, it is made up of those points where the value of potential is V. Where the value of potential is V. I know you are a bit confused right now. I know you are particularly confused. How can you come up with such a concept? How can you know whether all the points are lying on a surface? Why can't there be a hole in this surface? Like one point is at infinity, and where the potential may be V. I mean, at potential due to any charge configuration at infinity, it's considered to be 0. Okay, let it be at a very larger distance. So why can't it be a spike? It can be a spike. There can be a spike in the surface. See, every point, if the given function V is a continuous, a smooth function, which means even if there is a point at that, there can't, I mean, if it's a smooth function, there isn't any chance of getting a point, but still the surface could be of any shape. It could be like, it could look like your I don't know what it is called, what it looks like, but it could look like anything. I don't know what it is. It could be a surface like that. It could be a surface like the potatoes outside. It could be your I don't know, your just your a loaf of spinach, or it could be a piece of bread. The shape could be like that of a piece of bread, the outer surface of the piece of bread. It could be a pucka sphere, a Schur sphere. It could be cube. It could be cube. It could look like peanut, the shell of a peanut. See, it could be anything. It could look like dumbbell, the dumbbell you use. I mean, there are no notations already. It's just the surface. Okay, it's just every drawing I draw actually are meant to the thing you're supposed to take is only the surface, the outer surface. Okay, nothing inside. It's all hollow. It could be closed, it could be open, it could be anything. Okay, it could be just anything. So that's what I mean. What I mean is, it's just a surface. So how do you calculate the equipotential surface? So what I basically mean is, if suppose you have a charge here, let me go with a point charge. Suppose Q is a point charge. So you have a point charge over here. If you have a point charge Q, how do you define equipotential surfaces for this point charge Q? That should be your next question. So it basically means it is a surface that consists of points. Okay, it is a surface around the charge Q, where the value of potential is constant, has the same value everywhere on that surface. So how do you define this? So basically, a point charge Q, the potential due to a point charge Q can be given by, as you know, you have a point charge and at a distance, say I can call the distance to be like r, and the potential at this point r, at the distance r, will be V equals, you know, it's simple as kq over r. As you know, k is fixed, q is already fixed. Then the only variable that dictates the potential is the radius, the distance from the charge to that point. Okay, so how can you keep this constant? Yeah, exactly what you are thinking. Suppose you have another point here, say here, it's again at a distance, say r, from that given charge. At this point the potential again will be, let me call this v0, okay, and at this point also the value is kq over r, which is again v0. Can you find another point where the potential is same? Exactly. In between you can have another point over here, over here, over here. So every point at an equal distance from this given point charge, all the points which lie at an equal distance from a point, you have a set of points. See those set of points where the first point was this m1, m2, you have m3, m4, m5, m6, m7, etc., m1000. You have so many points, so you have a huge number of points which are equally distant away from this given point charge. It does not only lies on this two-dimensional plane, it also extends to your side. Imagine a spherical shell, or just imagine a sphere whose hemisphere is bulged out of your screen, and the rest of the hemisphere is lying below. So it's actually a sphere. A sphere is the only geometric figure which is whose points on the sphere are equidistant from a central point, and that central point is where our q is, okay. That q is where the central point of our sphere is. So you have this central point and all you have is a sphere. You have a sphere of radius r. So this sphere is actually a surface. So this sphere is actually a surface, and that surface represents one equipotential surface of this. So because you had fixed the radius, and by fixing the radius you made the potential at the distance to be v0, and you went on to define all the points, and you ended up getting is a collection of points which lies on a sphere. So you had a sphere, and this spherical surface is now your equipotential surface, is now an equipotential surface, because at every point on this surface, let me use green so you can see clearly. On every point on this spherical surface, the value of potential V is V0. So that is just one equipotential surface. What about you had instead of R, you moved a little bit further and you defined another sphere of radius r prime. So you have your next equipotential surface, which means r, which is a continuous parameter, could be varied as much as you like, and you would end up with a very huge number of equipotential surfaces. So equipotential surface around a point charge are actually in fact spherical surfaces. So you have so many. See, in the first case it was v0, and in the second case, in the second sphere, it would be some other value, v0 prime. In the third one, it could be v0 double prime, I don't know. So the potential at each equipotential surface has different values. So if you have two spheres, suppose if you had a point charge q, you had defined one equipotential surface, and that equipotential surface is defined by the value of the potential, and that potential is say v0, and now you had another equipotential surface, say here. Let me just use red, because red and green combine to good contrast. So this surface had a potential v00, I don't know, I can call it v0. I mean, it's not clear, right? So let me just write it to small. This surface can be represented by its potential, and that potential means the value of potential on its surface at any point on this surface. So you have this equipotential surface 1, and not E1, but let me call it S1, and you had this second one, you call it S2. There is a potential V0 on every point of S1, and there is a potential V00 on every point on S2. Okay, S2. So there is a difference in potential. So you have a potential difference. You have a potential difference. Potential difference. See, one more thing. So let me ask you a question. If you had this a certain charge configuration, and you somehow got a weird shape of this was say 1. See, this is no more a point charge. Okay, I am just talking about some random surface, I mean some random charge configuration, and related to that charge configuration, S1 is one of its equipotential surface, and the potential on that surface would be say V is equal to V1. I don't know, every point, suppose here, so every point on this surface has the potential value V1. My question is, there is what is the potential difference? So we can define another quantity, basically the most physical quantity among the talks of physics is the potential difference, because that's the most important one which we require. See, if you want to define potential difference, what do? You just subtract the values of potential at those points. Okay, you just subtract the values of potential at those points. So suppose you had a potential, a point here P1, and you had another point P2 on the same surface. My question is, what is the potential difference between these 2 points? So you do is you perform this subtraction. Value of potential at P1 is, since it is on S1, the value of potential would be V1, so V1. And what about P2? It's also on S1, so what is the value of potential on at P2? It's again V1. And what do you get after subtraction? You get is 0, which means at any 2 points on the actually this was an obvious fact, but still I just wanted to point you to it. So if you have any two points, or just the potential difference delta V at any 2 points of a given equipotential surface, EPS in short, is going to be 0. Now what implication does this have? So before you want to learn about the implication of that, it's basically you need to understand what does the physical significance of potential difference is. The physical significance of potential difference. The physical significance of potential difference is PD, potential difference delta V. What's it? You had a certain charge configuration, okay, and you had 2 points, say M1, and another point M2. Here the potential was V1, and here the potential was V2. Okay, what does V1 and V2 actually individually mean? V1 means it is the amount of charge, amount of energy required to bring a unit charge from infinity to that point. And what does V2 mean? It means it is the amount of energy required to bring another unit charge, or the same unit charge, from infinity to that point M2. So basically, since the amount of energy is in this case is V1, and the amount of energy is V2, and there is a difference in the value, that means V1 is not equal to V2, so there is a difference. So what does delta V stands for? It stands for, you can go with V1 minus V2 or V2 minus V1, it does not matter. So it's all about the magnitude, or There is there is a meaning for the sign also. I will explain that later. But let me just call it V1 minus V2. Okay. So there is a potential difference between these 2 points, and the potential difference is found to be V1 minus V2. What does that mean? It means there is a difference in energy required to bring that charge from at point M1 and at point M2. There is a difference in energy to bring a unit charge. So which means you might want to work more to bring it to M1, and you might want to work less. Okay, so there is the difference, which means if you are standing at point M1, I mean you have this unit charge at M1 and you bring it to point M2. What is the work done? What will be the work done to move the charge, the unit charge from V1 from M1 to M2? Which means whether you are bringing the charge to M1 or M2, you are bringing it from infinity. So which means if you want to bring the charge to say M2, you do a work V2 because it's unit charge. I am talking V2 because it's a unit charge. Okay, remember, whenever I say V2, it means the amount of energy for a unit charge alone. Okay, not for any charge. It's just a unit charge. Now if you want to move this charge from M1 to M2, how much M2 to M1, how much energy is required? From infinity, see, whichever path you bring the charge, you need to do the same work V1. So which means from M2 to M1, the amount of charge the amount of extra energy required will be actually delta V. See, that's the sense, because from here, from this equation for delta V, you know what is V1. See, the energy required to bring the charge from infinity to M1 would be V1, and that energy is just independent of the path, whether you come from this side or from this side or that side, it doesn't matter. So from this equation V1 is V2 plus delta V. So delta V now has some physical meaning. It is the difference in energy between these 2 points. So delta V is actually the excess energy that you will have to add or supply to the unit charge for it to move from between the respective 2 points. So basically it means if you have a point M1, if you have another point M2, and you know the potential at this point V1, and you have another value for potential at M2. So if you want to move a unit charge, okay, not any charge but a unit charge from M2 to M1, the amount of work done or the amount of energy that needs to be supplied will be equal to delta V, which will be equal to nothing but the potential difference between the 2 charges. Okay, I mean not the charges, potential difference between the 2 points. So what about another case? The case is if you have a charge, say Q. What is the energy? What is its energy? What is its potential energy at M1? It is QV1. What is the potential energy of the same charge at M2? It is QV2. So this is the energy required for the charge Q to be brought to M2, and QV1 will be the amount of energy required to bring it to the point M1. So if you bring it from infinity and you go to point M2 and then you go to point M1, what happens is, to bring it to the point M2, you have to do a work of QV2, and from there to M1 you will have to supply this extra energy delta V on a unit charge, which means for the entire charge you will have to supply this much of energy. this much of qv2. So that this is the energy, okay, extra energy required. So you can calculate it like that too. I mean, you have a system at a given potential energy PE1, and I mean PE1, there was I mean, there are 2 points m1 and m2, and at m2 the potential energy of the system, the charge is PE2, which was found to be qv2, and the potential energy of the charge at m1 is qv1, and you move the charge from m2 to m1. What is the so what is the amount of energy required? If it is a static system, if it is a static system, the amount of energy required will be nothing but basically the difference between the potential energies, PE2 minus PE. I would like to write it as PE1 minus PE2. So what is PE1? It is QV1 minus QV2. So bringing out the common charge, Q V1 minus V2, Q times V1 minus V2, and V1 minus V2, what does it stands for? It stands for the delta V, the potential difference between 2 points. So that's it. So that's the case. See, where does this apply? This applies to cases like you have an atom. If you have a nucleus, okay, you have a nucleus, and for the sake of simplicity, let us consider the nucleus of a hydrogen atom. If you have a hydrogen atom, then hydrogen atom has this isotope called protium, and which has only one proton at its center. So you can have an equipotential surface around it, and which will be a sphere. And so basically, if you have an electron on this equipotential surface, what will be the energy required for the charge, for the electron to move from this point P1 to this point P2 on that equipotential surface? What will be the energy required? What is the energy required to move this electron from P1 to P2 along the sphere? The answer will be, since the potential at P1 and P2 are same because they are points on an equipotential surface, the potential difference will be 0. If potential difference is 0, the energy to move electron from P1 to P2 will be E times delta V, and delta V, since delta V is 0, E times 0, and the energy required will be 0. So there will be no energy required to move electron on that first shell, the spherical shell. Actually, this is a Bohr model. This is the Bohr model. So there is no energy required for the particle to move, or there will be no energy released or energy absorbed when the electron moves from P1 to P2. What about let us consider another shell, another equipotential surface. Consider another equipotential surface. Now you have an electron here. Say you have an electron here. Now the electron is on the surface. Suppose this surface be called K, and this surface be called L. Okay, K is the first equipotential surface and L be the second. See, this is not at all equivalent to any of those KLMN in the Bohr model, but still I am trying to give you some sense. That's why I am using these. See, this electron, I mean this electron and this electron, they are all indistinguishable. So it's just an electron. So electron one, we have one electron in this L surface, and you have you wanted to move the electron from this surface to that surface, this surface to that surface. Okay, any point on this surface to that surface. See, in the first, let Vk be the potential at every point on the first surface, and Vl be the potential at every point on the second surface. So what is the energy required for this process to happen, to bring the electron or to jump the electron from, so this is Vk, okay, so don't get confused. What will be the energy required to move the charged electron from Vl to surface L to surface K? You just want to find the potential difference. The potential difference is basically VL minus VK minus VL, and that's the potential difference. So what is the energy? Delta E is equal to E times delta V, which is Vk minus VL. So that is the energy required. But since our charge configuration, so that is the energy required to move the charge from a shell, I mean the equipotential surface L to K. My question is whether you will have to give energy or whether it will release energy. It depends on the sign here. If delta E was greater than 0, which is if the energy is positive, which means you will have to supply the energy. Okay. Yeah. I'm sorry. If the delta E is positive, which means energy will be gained. If delta E is less than 0, which is if the energy delta E is found to be negative, we will have to supply energy. But as you know, Vk, as you know, according to the potential due to a point charge, it stands like this: kq over r. And since r is less for k, the potential Vk will be larger. So Vk is greater than Vl. Since r is smaller and it's in the denominator, Vk will be larger than Vl. So if Vk is larger than Vl, which means delta V as per this definition should be greater than 0, and that means you will have to you will not have to supply any energy, but you will instead get is an energy output. So that energy output, how does where does that energy output appears? It appears as a it appears as radiation, and that radiation is what you call is the energy released during the electronic transition. So equipotential surfaces are very great ideas. It refers to a lot of it has a lot of physical meaning to it. We will explore about various types of physical significances, as well as various charge configuration and their associated equipotential surfaces in a later video. Let me just give you another example also for equipotential surface. Let me just consider a dipole. A positive and a negative charge. If I have a positive and a negative charge, this is a positive, this is the negative charge. What will be the equipotential surface of this system? The equipotential surface of this system will be, how can you draw that? So this will be this will be an assignment. I am going to assign you this. You can find it on your own assignment. Just try to draw the equipotential surfaces around a dipole, an electric dipole. Okay, you might want to just check in. I will give you the answer in the next video. I want to stop this. This was an introduction about equipotential surface, which is basically a very good concept, and we will be dealing with the relation between electric field and the potential using equipotential surface in the next equipotential surfaces in the next class. Thank you. it's a bit complicated one. So this will be this will be an assignment. I'm going to assign you this. You can find it on your own assignment. Just try to draw the equipotential surfaces around a dipole, an electric dipole. Okay, you might want to just check in. I will give you the answer in the next video. I want to stop this. This was an introduction about electrostatic equipotential surface, which is basically a very good concept, and we will be dealing with the relation between electric field and the potential using equipotential surface in the next equipotential surfaces in the next class. Thank you.